Come on, my dears, let us proceed further in chapter number 2. Actually, last time we had finished all the illustrations, but unfortunately, by mistake, the illustration number 7 was left out. It's a very simple sum. Let us do it. Just kindly read the statement of illustration number 7. Come on, read it. Tell me. We are given a straight rod of length small l and mass capital M. It rotates about an axis which is perpendicular to its length and tangential to any one of its two ends. And when it does so, what is the moment of inertia of that rod and what is the radius of gyration, that both the values we have to find out. Let us find out this way. First of all, you consider this axis which is passing through center of mass of this rod and perpendicular to length of the rod. For such an axis, moment of inertia of this rod we had found out last time in the theoretical part, and it was found to be, remembered by formula, ml square upon 12, where m is mass, l is length of the given rod. Fine. Now about this new axis, I want to find out moment of inertia, but that new axis is tangential to this end and it is perpendicular to this length, and also it is parallel to this axis. And now perpendicular distance between these two parallel axes is, suppose small d, it will be half of the total length, half of L, that is why I have written here L by 2, correct? Fine. Now recall the result which we had obtained in parallel axis theorem. According to parallel axis theorem, I equals to IC plus MD square. I equals to IC plus MD square. Come on, IC. IC is ML square upon 12. IC is ML square upon 12 plus M. What is this square from here? This square would be, come on, L square upon 4. L square upon 4. Now simplify. In the LCM you can take 12. This ml square as it is. Come on, 4 3s are 12. So here you can multiply by 3. 3 ml square. 3 ml square plus ml square, that is 4 ml square. 4 ml square upon 12. So it is ml square upon 3. So this is the new moment of inertia of the same rod about this axis. Okay, fine. Now for any rigid body having any shape, having uniform material density, you know the formula of I in terms of radius of gyration. It was I equals to mk square. This right hand side as it is. Now m will cancel. K square will be equal to L square upon 3. When k square is L square upon 3, take square root. K will be L upon root 3. L upon root 3. So this is the radius of gyration. Fine. Now we go for beginning the MCQs from the exercise. Kindly read the statement of first MCQ. Come on, read it. Look, for one particle of a rigid body, they have given angular speed 12 radian per second. And now they have asked angular speed of another particle at the same moment. Then remember, whenever any rigid body performs rotational motion about stationary axis of rotation, remember, whatever is the angular velocity of a given particle, of any one particle, same is the angular velocity of any another constituent particle in that body. I mean to say, at a given instant of time, angular speeds of all the constituent particles are same. For one particle, if it is 12 radian per second, for another particle also it will be remaining same, 12 radian per second. So I have written here answer 12 radian per second. The reason is this: at a given instant of time, angular speeds of all the constituent particles are same. Correct? Fine. Now read number 2. Come on, tell me. They have asked about linear speed. Have you remembered we had derived scalar relationship between vector v and vector omega, and that scalar relationship was v equals to r omega. V equals to r omega. What is r? Perpendicular distance of a given particle from axis of rotation. At present it is 10 centimeter. What about omega? They have given 20 radian per second. Simplify. 2 and 20 into 10, that is 200. Because this value you are taking in centimeter, unit of this velocity would be centimeter per second. Had this been in meter, we could have written here meter per second. Right now this is in centimeter, so we are writing centimeter per second. Okay. Now read number 3. Read it. We are given minute hand. Which hand? Minute hand, or sometimes we call it minute arm in a clock, for which we have to find out angular speed. Come on. Average angular speed formula is average of omega equals to delta theta upon delta d. But for any hand, it may be second hand or minute hand or hour hand. For a given clock, in any clock, for a given arm, for a given hand, whatever is its angular speed, that remains constant. For second arm, it is the highest. For minute arm, it is lesser than that. And the slowest moving arm is the hour arm. Correct? But for a given hand, its angular speed remains constant throughout its rotation. Correct? So because this angular speed of a minute hand is constant, instead of average of omega, I just write only omega. Okay? Fine. Now this delta theta is angular displacement. Let that minute hand complete one rotation. Correct? Whenever any hand completes one rotation, naturally it undergoes angular displacement. How much? 360 degree or 2 pi radian. 2 pi radian. So I am writing from one rotation, I just transfer it into radian. One rotation is 2 pi radian. Divided by delta t, time taken to complete one rotation by minute hand, it is 1 hour. And 1 hour is 3600 second. Come on, rotation to radian and hour to second. Okay. Now simplify. Take this 2 in the denominator, denominator 3600 upon 2, that will be 1800. So answer is pi upon 1800. Pi upon 1800. Unit of angular speed is radian per second. Okay. Fine. Now instead of minute arm, suppose they are giving hour arm. Then for hour arm also you may allow one rotation. So here it will remain 1 into 2 pi radian as it is. But for hour arm, when it completes one rotation, come on, 12 hours are passed. How many hours? 12 hours. Time taken by hour arm to complete one rotation is 12 hours. So here you should write 12 into 3600. Got it? Had it been second arm, then here it will remain same 1 into 2 pi. But second arm takes only 60 seconds to complete one rotation. So at the time in the denominator you are supposed to write 60 seconds. Okay, fine. Now kindly read the statement of number 4. Read it. Omega equals to omega 0 plus alpha into t. Come on, time is given to you 4 seconds. At the end of 4 seconds, the angular speed they have given 64 radian per second. Because body starts from rest, initial angular speed is 0. Alpha as it is. Find out alpha from here. 64 upon 4, that is 16. Unit of angular acceleration is radian per second square. Okay, fine. Now read the number 5. Come on, according to Kepler's second law of planetary motion, we had obtained one result. Aerial velocity of a given planet is L upon 2m, where L is the angular momentum of that planet and m is mass of that planet. Right now, this angular momentum they have given 4 into 10 raised to 7 joule into second. And what about mass of a given planet? They have given 500 kilogram. Simplify, answer is 4 into 10 raised to 4. Now just take care while writing the unit. It is now area upon time. Unit of area is meter square. Unit of time is second. Okay. So this much is the aerial velocity of a given planet. 4 into 10 raised to 4 meters square upon second. Okay. Read number 6 now. Read it. Come on. According to law of conservation of angular momentum, L equals to I omega equals to constant. When I into omega is constant, come on, I1 omega 1 will be I2 omega 2. Come on, I1. We are talking about Earth. Earth we should take at present a sphere, solid sphere of uniform density. Then moment of inertia about an axis passing through its diameter is I equals to 2 by 5 mr square. So here I am writing I1 equals to 2 by 5 m r1 square. Omega formula is 2 pi by capital T. Because it is omega 1, I am writing 2 pi upon T1. This I2 is 2 by 5 m r2 square. 2 by 5 m r2 square. Omega 2 formula is 2 pi upon T2. Come on, 2 by 5 m, 2 by 5 m getting cancelled. Come on, 2 pi also getting cancelled. What is left? R1 square upon T1. Here R2 square. Now new radius has become, suppose, nth part of initial radius. Because of shrinkage of Earth, suppose radius decreases to nth part of initial radius. So I am taking at present R2 equals to R1 upon n. Then tell me R2 square will be R1 square upon n square. R2 square will be R1 square upon n square. 1 upon T2 as it is. Now R1 square will cancel. T2 will be T1 upon n square. T2 will be T1 upon n square. Okay. Come on. New periodic time of rotation would be 1 upon n square times initial periodic time of rotation. At present, what is the time taken by Earth to complete one rotation about its own axis? It is 1 day, that is 24 hours. Correct? And now, because of shrinkage of Earth, if its radius decreases to half of the initial radius, here they have given fourth part. Here they have given fourth part. If radius decreases to fourth part of initial radius, you can write R2 equals to R1 upon 4. R2 equals to R1 upon 4. Now we match this to, come on, n equals to 4. So right now value of n is 4. Value of n is right now 4. It's a square. 4 square is 16. 24 upon 16 will be 1.5, that many hour. Correct? This much will be length of the day if Earth shrinks and its radius becomes fourth part of initial radius. Okay? But they may ask the reverse condition. They may give, Suppose Earth expands, and because of expansion, suppose its radius becomes n times. If radius becomes n times, then you may write R2 equals to n into R1. R2 equals to n into R1. At that time, you will get it here T2 equals to n square into T1. T2 equals to n square into T1. And at that time, whatever value of n you are given, depending upon that, you can find out new length of the day. Okay. If radius becomes nth part, then new periodic time will become 1 upon n square times. If radius becomes n times, then new periodic time will become n square times. Got it? Fine. Now read number 7. Come on. Omega equals to omega 0 plus alpha into t. Come on. We are given 2 eggs, and if both the eggs are coming to rest after some time, then final angular speed must be 0. Initial angular speed as it is, but instead of alpha, see, as time passes on, the angular speed goes on decreasing, then only after some time both the eggs come to rest. Because angular speed decreases with time, there is actually angular deceleration, and mathematically we write it negative. So instead of alpha, I am putting minus alpha dash into t, and now transfer this, correct? From minus it will become plus, and now find out, look, alpha dash value, alpha dash is angular deceleration, its magnitude is alpha dash right now. Come on, tau equals to I alpha, instead of alpha I am putting alpha dash. Find out alpha dash, it will be tau upon I. Alpha dash is tau upon I into t, and that equals to omega 0. Find out t, I into omega 0 upon tau, I into omega 0 upon tau. What is this t? Time taken by given egg to come to rest, because we have taken final angular speed to be 0, correct? Now tell me, we are given 2 eggs, one is raw, another is boiled egg. Both the eggs, appearance wise, they are appearing same way. I mean, both the outlook is same for both the eggs. So from the outlook, we cannot find out that which one is raw, which one is boiled. That is why we are asked this question to find out using physics. Look, on both the surfaces, the anti-torque provided to them, because the angular speed goes on decreasing with time, there must be some friction here. So friction provided by both the surface is same. Both the eggs are same as far as outlook is concerned. Now tell me, one is raw egg, another is boiled egg. In a raw egg, the fatty substances are present in the form of liquid. So here there is a liquid, and if this fatty substance is in the form of a liquid, the moment you try to rotate this egg about this axis, it will so happen that because of centrifugal forces, the particles of that fat will just move away from axis. And if particles are moving away from axis, naturally in this formula of moment of inertia, all these perpendicular distances of various constant particles from axis of rotation would increase. If these perpendicular distances would increase, naturally value of I will increase. When value of I increases, then come on, L equals to I omega equals to constant. When I into omega is constant and value of I is increasing, then value of omega must be decreasing. Okay. And now tell me here, for raw egg, value of I is more. For raw egg, value of I is more. So when value of I is more, then time taken to come to rest will be more. So raw egg will come to rest later. But we are not asked to find out that which egg comes to rest later. We are asked which egg comes to rest earlier. Come on. Instead of raw egg, now if you take boiled egg, suppose boiled egg, then in case of boiled egg, the fatty substances are in the form of solid state and they do not move away from the axis of rotation. When the particles of these fatty substances in the boiled egg do not move away from axis of rotation, its moment of inertia comparatively will be less. When moment of inertia is less, then time taken to come to rest will be also less. So boiled egg would come to rest first, and later this raw egg will come to rest. In examination, they may ask reverse question. They may ask which egg would come to rest later. Then answer is raw egg. Right now they have asked which egg comes to rest first. It is boiled egg. Because of less moment of inertia, time taken to come to rest is also less. Okay, fine. Now read number 8. Read it? Come on. We are given two substances for which torques are applied same. So tau 1 equals to tau 2. According to formula, tau equals to I alpha. So here I am writing I1 alpha 1. Here I am writing I2 alpha 2. For first substance, it is hollow cylinder. That's why moment of inertia is I equals to mr square. Alpha 1 as it is. Second substance is solid sphere. So I should write I equals to 2 by 5 mr square and into alpha 2. Come on. Masses of both the substances are same. Radii are also same. M and r square will be getting cancelled. Find out alpha 2. It will be 5 by 2 alpha 1. 5 by 2 alpha 1. Because this multiplier is greater than 1, we can say alpha 2 greater than alpha 1. Alpha 2 greater than alpha 1. Okay. Now read number 9. Come on. For a solid cylinder to roll down the slope without slipping on a slope of angle theta, you must remember the condition which we had obtained. Mu s must be greater than or equal to 1 by 3 tan theta. 1 by 3 tan theta. Okay. What is this mu s? Coefficient of static friction. They have given in the statement 0.35. 1 upon 3 tan theta. Let us find out. 1 upon 3 as it is. Tangent of theta. Theta. Angle of slope, they are given 30 degree. Tangent of 30 degree is 1 upon root 3. 1 upon root 3. Root 3 value is 1.732. This 1 by 3 as it is. Simplify. Answer is 0.192. And tell me, 0.35 is definitely greater than 0.192. Because this is greater than this, mu s is at present greater than 1 upon 3 tan theta. Because mu s is greater than 1 upon 3 tan theta, this condition is satisfied. And because this condition is satisfied, solid cylinder will definitely roll down the slope without slipping. Wait. Here instead of solid cylinder, they may give you other substance, say thin circular ring. At that time, the condition was mu s must be greater than or equal to, remembered, 1 by 2 tan theta. What was the condition? 1 by 2 tan theta. If they give suppose solid sphere, what was the condition? Mu s must be greater than or equal to 2 by 7 tan theta. 2 by 7 tan theta. Okay. So depending upon the different type of object, you may have this condition in different manner. Okay. Now read number 10. At the bottom of the slope, on which factor does the velocity achieved by the body depends? Let us find out. We are given solid cylinder. Okay. Come on. As the solid cylinder rolls down the slope of a height h, as it moves from top to bottom, by that time it loses gravitational potential energy. How much? mgh. And at the loss of potential energy, it gains kinetic energy. What is the gain in linear kinetic energy? Half mv square. What is the gain in rotational kinetic energy? Half I omega square. Correct? Here v is velocity of a body at the bottom of the slope. Omega is angular velocity of a body at the bottom of the slope. Now this mgh as it is, half mv square also as it is, 1 by 2 as it is. But what about moment of inertia for a solid cylinder? I equals to 1 by 2 mr square. I equals to 1 by 2 mr square into omega square. Fine. mgh as it is, half mv square as it is, 2 2s are 4 m r square omega square. Wait, do you know v equals to r omega? V equals to r omega. So take squares on both the sides. V square equals to r square omega square. V square equals to r square omega square. Speak reverse. Instead of r square omega square, I can write v square. Instead of r square omega square, I can write v square. Correct? Now mv square we can take common. Inside the bracket 1 by 2 plus 1 by 4, it is 3 by 4. Fine. M will cancel. V square will be 4 by 3 gh. 4 by 3 gh. Take square root on both the sides. Square root of this is v. Square root of this is under root 4 by 3 gh. Now we can see here this velocity of solid cylinder at the bottom of the slope, when it comes down, rolling without sliding, rolling without slipping, at that time the velocity of solid cylinder at the bottom of the slope is under root of 4 by 3 gh. You can say this velocity depends on height of the slope. It depends on height of the slope. Fine. Now suppose instead of solid cylinder, if they give thin circular ring, then here you will make the change. Instead of I, you will write only mr square, not half mr square. You will write only mr square. Got it? This 1 by 2 as it is. This 1 by 2 as it is. But instead of I, in the bracket you will write only mr square. At that time, final result is v equals to under root of only gh. V is equal to under root of gh. And suppose you are given, say, solid sphere, then this 1 by 2 as it is, in bracket value of I is 2 by 5 mr square. And at that time, this velocity comes out to be under root of 10 by 7 gh. Under root of 10 by 7 gh. Okay. In any case, for every body, this velocity at the bottom definitely depends on height of the slope. Okay. Fine. Read down number 11. Come on, read it. Moment of inertia for a solid circular disc or for a solid cylinder about an axis passing through its center and perpendicular to its plane is I equals to 1 by 2 mr square. M is the mass given to you 4 kilogram, radius is 2 kilogram. Simplify. Answer is 8 kilo, unit of mass is kilogram, unit of radius square, that is meter square. 8 kilogram into meter square. Got it? Read number 12 now. Read it? Come on. You know, earth is flattened at the poles, bulge at the equator. That's why the shape is like this. Now in the winter season, the whatever quantity of ice is present here at the poles, if it gets melted, then that melted ice would come down and the particles would be getting spread over the surface of earth. And if they come at the equator, what will be the effect on length of the day? Come on. Whether particle is here or here, its mass remains constant. But if particles is here nearby the axis, then distances would be less. And if the same particles, if they come here, their perpendicular distances from this axis would increase. And as this perpendicular distances would increase, naturally value of I will increase. If value of I increases, then angular speed will decrease, because I into omega remains constant according to law of conservation of angular momentum. If I into omega is constant and value of I increases, omega will decrease. Don't you know formula of omega? Omega equals to 2 pi by capital T. When omega decreases, capital T will increase. Capital T will increase. That is, time taken by earth to complete one rotation would increase. That is, length of the day would increase. Fine. Now read number 13. Come on. Because resultant external torque exerted on a system is 0, given to you in the statement. Whenever resultant external torque is 0, come on, total angular momentum of that system would remain constant. Correct? Fine. Read number 14 now. Read it. Omega equals to omega 0 plus alpha t. What is omega? Angular speed at the end of some time. They have given 240 revolution per second. 240 revolution per second. This is the initial angular speed. Because the body starts from rest, come on, initial angular speed is 0. Alpha as it is, time is given to 4 minutes. 1 minute is 60 seconds. Convert minute to 60. Multiply by, convert minute to second. Multiply by 60. Come on. Now this is 0 only. This is 16 to 4, that is 240. Find out alpha. 240 upon 240, it is 1. But unit of angular acceleration right now, just take care. Because you have taken this omega in revolution per second square, the unit of angular acceleration would be revolution upon second square. Revolution upon second square. Fine. Read number 15 now. Read it. We are asked to find out a ratio of values of moments of inertia for two substances. One is solid sphere, another is a thin, extremely thin hollow sphere having very thin wall. We call it spherical shell. Extremely thin spherical shell. Come on, for a solid sphere, what is the moment of inertia? 2 by 5 mr square. For extremely thin hollow sphere, it is moments of inertia is 2 by 3 mr square. 2 by 3 mr square. For extremely thin spherical shell, remember, moment of inertia about an axis passing through its diameter is 2 by 3 mr square. Now 2 will cancel, mr square will cancel. This denominator will become numerator. So now it will be 3 by 5. 3 by 5. So required ratio of two values of moments of inertia is 3 by 5. Read number 16 now. Read it. I equals to 1 by 2 mr square for a solid cylinder. Let it be I1 because I am talking about moment of inertia of first substance, and you also know that I equals to mk square, where k is radius of gyration. For first substance, let it be k1. For second substance, I am taking I2 because it is given to me hollow cylinder for which, come on, mr square. Actually, it should be thin hollow cylinder, extremely thin hollow cylinder. Such a thin cylinder such that whether you take inner radius or outer radius, it should be same. Okay, fine. Now tell me, for second body also you can write I equals to mk square. Here I am writing k2 square because masses they have given same. Fine. Radius also they have given same. Now just take the ratio this way. This upon this, it will be this upon this. But when you take this upon this, mr square will cancel, giving you 1 by 2. When you take this upon this, will cancel, k1 square upon k2 square, k1 square upon k2 square. Come on, take square root. Here when you take, come on, k1 upon k2, when you take square root here, 1 upon root 2. Got it? Fine. Read number 17 now. Read it. We are given extremely thin circular ring which, come on, performs rotational motion about an axis passing through center perpendicular to its plane. Moment of inertia you can write this way, I equals to mk square. This is the moment of inertia of a given system in the first condition. In the second condition, let it be I2. Now what we do, we have two identical point masses, say each having mass small m, and we just place them very slowly at the diametrically oppositely located points on the rim of the ring. And when we do that, what is the final angular speed? That is what we have to find out. Come on. I2 equals to, come on, according to this formula, mass into square of radius of gyration. But now what is the total mass of the system? Mass of this ring is capital M, and summation of these two masses would be m plus n, that is 2m. So now this gives you total mass of the entire system into k square. Because the ring remains same, for a shape of the body, if it is remaining same, then radius of gyration would remain same. Fine. Here also k square, here also k square. And now you know law of conservation of angular momentum. L equals to I omega equals to constant. L equals to I omega equals constant. From this result, I into omega is constant. You can write mathematically I1 omega 1 equals to I2 omega 2. What is I1? I1 is mk square. I1 is mk square into omega 1. Come on, I2. I2 is m plus 2m. M plus 2m into k square into omega 2. And now k square will cancel. Just cancel k square. And then, come on, k square is getting cancelled. Then find out omega 2. Omega 2 would be m upon m plus 2m into omega 1. But the initial angular speed they have given as only omega. So instead of omega 1, I am just putting omega. So this is the final answer where you found out angular speed of the ring in the final condition. Okay. Fine. Read number 18 now. Come on. What is rotational kinetic energy formula? Half I omega square. But what is this I? Moment of inertia. But the given body is thin circular ring for which I equals to mr square. So final formula for rotational kinetic energy is half mr square omega square. Got Got it? Read number 19 now. Read it. We are asked to find out a ratio of two angular speeds. Come on. One for geostationary satellite, another for Earth. Come on. Omega by formula it is 2 pi by capital D. Here it is omega 1, so I should write 2 pi upon T1. Here it is omega 2, then I should write 2 pi upon T2. 2 pi will cancel. Denominator will become numerator, so T2 upon T1. Now, about geostationary satellite you will be taught in the next chapter. It is such a satellite which orbits around Earth in the equatorial orbit, and its periodic time of revolution is kept equal to periodic time of rotation of Earth. So, periodic time of revolution of geostationary satellite is just equal to periodic time of rotation of Earth, which we know it is 24 hours. So, this is the periodic time of revolution of, say, geostationary satellite. It is 24 hour, and for periodic time of rotation of Earth is also 24 hours. So, T2 is also 24 hour. 24 hour upon 24 hour ratio is 1. So, required ratio is omega 1 upon omega 2 equals to 1. Okay. Read number 20 now. Come on, according to Kepler's second law on planetary motion, don't you know, aerial velocity of every planet remains constant. So, dA by dt equals to L upon 2m, and that remains constant. Now, we begin the numericals from exercise. Just kindly read this statement of first exercise sum. Come on, read it. Theta equals to omega plus omega 0 by 2 into t. Remember this formula. How? This is the angular displacement, this is average angular speed into time. The way in first semester you had written d equals to v plus v0 by 2 into t. Linear displacement equals to average linear speed multiplied by time. Similarly here, angular displacement is equal to average angular speed multiplied by time. Come on. At the end of certain time, they have given this angular displacement 600 radian. What about omega 0? We want to find out. After 12 seconds, the angular speed becomes 100 radian per second divided by 2 as it is. Simplify, you will get the value of omega 0, 0. Correct? Fine. And now omega equals to omega 0 plus alpha d. Omega equals to omega 0 plus alpha d. What is the value of omega? They are given 100 radian per second at the end of 12 seconds. Initial angular speed we have found out it is 0. Alpha as it is, this time is 12 seconds. And now find out alpha, it will be 100 upon 12, that is 8.333 radian per second square. Okay. Kindly read now statement of number 2. Come on. Theta equals to omega 0 t plus half alpha t square. What is this angular displacement they given? 100 radian. What about initial angular speed? 20 radian per second. Time they are given 10 second. 1 by 2 as it is, alpha we require. Time is given to 10 seconds. Simplify, find out value of alpha. It comes out to be minus 2 radian per second square. Negative sign indicates decrease in angular velocity with respect to time. That's why it is called angular deceleration, and mathematically its value is negative. Omega square minus omega 0 square equals to 2 alpha theta. Third equation of rotational motion performed about stationary axis of rotation with constant angular acceleration. Come on, final angular speed must be taken 0 because they have asked that how many rotations will get finished before coming to rest. So once the body comes to rest, final angular speed is 0. Initial angular speed they have given 20 radian per second, and then 2 as it is, alpha we have found out minus 2, theta we require. From this you will get theta equals to 100 radian. But they have not asked the angular displacement, they have asked how many rotations are finished before it comes to rest. So when you want number of rotations from radian, you should go for number of rotations. What you should do? Divide radian value by 2 pi. Divide radian value by 2 pi. See, one rotation is 2 pi radian. One rotation is 2 pi radian. So from rotation to radian, you should multiply by 2 pi. Now you are going from radian to number of rotation, then you should divide by 2 pi. So radian value is right now 100, and that value I am dividing by 2 pi. 100 upon 2 is 50. Pi is there in the denominator. So these many rotations will be there before the body comes to rest. Got it? Read now number 3. Read it? Look, tau equals to I alpha. Tau equals to I alpha. Tau as it is. Moment of inertia for a hollow cylinder, it is I equals to mr square. Angular acceleration from here, find out alpha, it will be omega minus omega 0 upon t. Omega minus omega 0 upon t. This mass is, come on, mass of the given hollow cylinder is 20 kilogram. Radius is 1 meter. Final angular speed is 25 radian per second. Initial angular speed is 5 radian per second. Time is given to 4 seconds. Simplify. Torque comes out to be 100 Newton into meter. Unit of torque you should write Newton into meter. And now work done by constant torque in case of rotational motion. What was that formula? W equals to tau into theta. Tau into theta. Tau as it is. What about theta formula from here? Theta is how much? Omega plus omega 0 by 2 into t. Omega plus omega 0 by 2 into t. Come on. Tau as it is, theta formula. Same formula written here. Omega plus omega 0 by 2 into t. What about torque? We have found out 100 Newton into meter. Final angular speed is 25 radian per second. Initial angular speed 5 radian per second divided by 2 as it is. This time you are given 4 seconds. Simplify. Answer is 6000 joule. SI unit of work done is joule. Correct? Read now number 4. Read it? Let us find out first of all linear momentum of a single particle. You know by definition it is mass into linear velocity. Mass they have given 50 units. What about linear velocity? They have given 2, 3, 6. Fine. 52 is 100. 53 is 150. 56 is 300. Okay. And now they have asked angular momentum of a single particle. By definition we know vector L equals to vector R cross vector P. But then tell me, Had it been vector A cross vector B, you have studied its formula in first semester. How are you writing? Come on. 3 by 3 determinant. Come on. I hat, J hat, K hat, AX, AY, AZ, BX, BY, BZ. Here also 3 by 3 determinant. Come on. I hat, J hat, K hat. And then I am supposed to write 3 mutually perpendicular components of first vector in this order, and 3 components of vector are position vector. They have given in the statement 4, 6, 12. What about vector P? Its 3 components we have found out: 100, 150, 300. 100, 150, 300. Fine. And now come on. Before simplifying this, just you can take 25 common from the third row. Come on. If you take 25 common, then 100 upon 25 it is 4, 150 upon 25 is 6, 300 upon 25 is 12. And now you can see second row and third row are same. In any 3 by 3 determinant, whenever any 2 columns or any 2 rows are same, its expansion comes out to be 0. But because there are right now vectors, this expansion would come out 0 vector. That's why in place of this I have written 0 vector into 25 will give you 0 vector. Whenever any vector is 0 vector, its magnitude is also 0. Okay.